Hi and welcome. Tonight, Midnight is here to assist us in learning Chapter 12 and Chapter 13. Ariana is also joining us as our second assistant. Okay, so today we're going to start talking about Chapter 12. And the topic in Chapter 12, at least in Section 12.1, which we're going to talk about today, is indefinite integrals. Okay. All right, now, in the past, we have been learning, and everyone who's listening to this video is really good at finding derivatives. And so, given something like y equals 5x, we know that the derivative is 5. Okay? And every one of you who's watching this video right now is really good at taking derivatives. What we're going to do today is I'm going to be asking all of you to turn your camera upside down or possibly stand on your head, because everything that we have been doing, we're going to do backwards. Okay, so here's our first example. Given that our derivative is 8, the question is, what was the original function y? Okay. Now, if we were in class, I'd ask you to turn to your neighbor and say hello and tell your neighbor what the original function was. Well, you probably are not quarantined with anybody else who's in our class, so maybe tell your dog, tell your roommate, tell somebody in your house what the original function is if the derivative is 8. Okay, so think about that for a second. Okay, now, many of you might have said, well, the original function is y equals 8x. And that is absolutely true. That when you take the derivative of 8x, you get 8. And that's awesome. What about y equals 8x plus 3? Well, the derivative of 8x is 8, and the derivative of 3 is 0, so the derivative of 8x plus 3 is also 8. Or, what about y equals 8x plus 72? Its derivative is also 8. Or even y equals 8x minus 5. Derivative is still 8. So actually, when you have a derivative of 8, there are a lot of original functions whose derivative is 8. And the way that we compensate for having all of these different functions that all have a derivative of 8 is, instead of writing them all out, because there's infinitely many, one for every single added on constant that you can have, we write, or we say that y is equal to 8x plus c, where c is a generic constant. All right, so if we're given a derivative and we want to find the original function, at least in this case, we can write down the 8x, but then we want to add on that plus c, because we don't know if there was some constant on the original function, because when we take the derivative, we get 0. Okay, so let's look at another example. F prime of x is equal to 8x to the third. So the question is, what was the original function? And I encourage you to pause the video for a minute and think about, what would the original function have to be so that its derivative would be 8x to the third? All right. So I just wrote down 2x to the fourth. I hope you paused it. I hope you tried that on your own first. And I'm going to double check. If I take the derivative of 2x to the fourth, I bring the 4 down in front, I get 8. And then I have 1 less on the power, x to the third. Now, I don't know. There might have been a number added on to the end of this function, because when I take the derivative of any constant by itself, its derivative is 0. So I always add on that plus c at the end, because I don't know if there was a constant on the original function, because when we take the derivative of a constant by itself, the derivative is 0. Okay. So this idea or this process of finding the original function when we are given the derivative, this is called anti-differentiation or integration. So finding the original function f of x from the derivative is called anti-differentiation. In other words, finding an antiderivative. Or another word for this is integration. Or the verb for integration is integrating. Okay, now in our first two examples of anti-differentiating or integrating, in other words, finding the original function from the derivative, we kind of did this kind of haphazardly. Like you used your ideas from when we learned about derivatives and said, okay, if the derivative is 8, then the original function must have been 8x. Then we added on the plus c because of that constant. And you can kind of work backwards where if you know your derivative, you can find the original function. But we'd like to be able to do this in a little more streamlined fashion. So that's what I want to talk about next. Okay. All right, so as we think about this, I want to talk about a very old school technique. All right, so way back in the days before we had Google Maps and in the days before you had a GPS on your phone where you could just type in an address and the GPS would tell you how to get to where you're going, let's say that you wanted to go to your friend's house. And this is a new friend and they've invited you over for dinner. And so we're talking old school here, so they probably picked up the phone with a little curly cable attached to it and dialed your number on the rotary phone and said, hey, can you come over for dinner? And you say, sure, how do I get to your house? And your friend says, I can tell you. Do you have a piece of paper and a pencil? And then your friend lists, step by step, all the steps it takes to get to their house. Turn left onto this street. Go 2 miles north. Turn right onto this street. Then take a left and then another left and then a right, and my house will be right there. And you say, great, you write down all the instructions, and then you hop in your car and you start following the instructions step by step. Great. Okay, so you go to your friend's house, you have a great time, you enjoy dinner, and at the end of the night you say, thanks for having me over, I'm going to head home now. And you go back out to your car, and remember, no GPS, no cell phone, okay? And right now you're sitting in the middle of suburbia where all the houses look the same, and you have no idea, suddenly it's dark, and you have no idea how to get out of your friend's neighborhood. So what do? Well, you pick up that piece of paper where you'd written down the instructions to get to the house, and you start at the bottom, and you look at the last instruction which said, turn right onto such and such a lane. Well, what you do is you backtrack, and wherever you were told to turn right on the way in, you now turn left to leave. And anywhere where you originally turned right to come in to your friend's house, you now go the opposite direction on your way out. So to leave the house, you undo from the bottom up everything that you had originally done. So let's apply that now to this idea of derivatives and then finding an antiderivative. All right, we're going to do this by looking at an example. So, for example, if y equals 5x to the fourth, then its derivative is 20x to the third. Okay. Well, we lost our assistant. She went down for a nap. So here we are back here with our example. So remember, what we're doing here is that we are thinking carefully about what it means to take a derivative. So everyone who's watching this video is good at finding derivatives. So the derivative of 5x to the fourth is 20x to the third. And I want to think carefully about how we came up with that derivative. So the first step in finding our derivative is that we took the power that was up here, the exponent, we brought it down in front, and we multiplied by whatever that number was in front. So we took that 4 times the 5, and it gave us 20. So the first step is that we multiply the number in front by the exponent. And once we did that, once we bring the number down in front, multiply the 5 times the 4 gives us 20, then we subtract 1 from the power. So step 2 is to subtract 1 from the power or from the exponent. Exponent. Okay, so these are our 2 steps for finding the derivative. Now, like what I talked about when you went to your friend's house and then you had to undo the list of instructions to get there, we want to undo this process of finding the derivative. So to find the antiderivative, or to undo this process, we're going to start at the bottom of this list and undo or do the opposite of each step. So to find an antiderivative, step 1, well, at the bottom, at the end of finding a derivative, we subtracted 1 from the power. The opposite of subtraction is adding. So step 1 is to add 1 to the power, or to the exponent. Okay. After we do that, we work our way back up. The next step, or the first step in finding a derivative, was to multiply the number in front by the exponent. The opposite of multiply is divide. So our step 2 of finding an antiderivative is to divide the number in front by that new power. Okay. All right, so let's think about that in terms of this particular example. In the example we just saw, let's see, if we have y prime is equal to 20x to the third, then if we follow our steps for finding the original function, the first step is to add 1 to the power. So instead of x to the third, I have x to the fourth. Step 2 is to divide the number in front by the new power. Now the number in front was 20, and we're dividing that 20 by our new power of 4. Now 20 divided by 4 is 5, so we end up with 5x to the fourth. So if our derivative is 20x to the third, the original function was 5x to the fourth. Now, I do have one extra thing I need to add on here, and that is a plus c, because there could have been a constant at the end that I didn't know about, and I need to account for that by adding the plus c. Okay, let's do another example. So our instructions are to anti-differentiate. And our job is to anti-differentiate x squared. Now, when I see that word anti-differentiate, what that means is that we want to think of that x squared as a derivative. So this means think of x squared as a derivative, and we want to find the original function. Okay, so according to our steps over here, the steps that we laid out. Our first step is to add 1 to the power. So our power, we had a power of 2, so now we have a power of 3. And then I want to divide the number in front by the new power. Now, in this case up here, there's no number in front, but whenever there's no number written down, there's an understood 1 in front of that x squared. So I'm going to divide the number in front by my new power. So I have 1/3 x to the 3rd. And then I add on that plus c because there could have been a number on the original function whose derivative is 0. Okay, so the cool thing about this is, even though this is a new process, you can always check your work, because you can check that when you take the derivative of 1/3 x to the 3rd, and we're more comfortable with derivatives, you bring that 3 down in front, 1/3 times 3 is 1, and then you have x to 1 less is x squared. The derivative of the plus c is 0. Okay, so that's our first example. Before we do, we're going to do a few more examples here, but before we do, I want to talk to you about some notation. Some notation that goes along with these antiderivatives, and here's what it looks like. So this notation, there's this long, stretched out, skinny s, and then I have some kind of a function in the middle. In this case, in this example, I'm writing 4x to the 9th. And then there's this dx at the end. Okay? And this notation that I read here, I can read this as this is an example of an indefinite integral. And this notation says, find the antiderivative of 4x to the 9th. Or in other words, we can think of this thing in the middle, this formula in the middle, as the derivative, and we want to find the original function. Okay. Now, let's go back up to this notation up here. This long stretched out s and the dx at the end, those are always paired together, kind of like parentheses, in the sense that you're not going to see a long stretched out s without a dx at the end, and you're probably not going to see a dx without a long stretched out integral. So as a pair, these two pieces together tell us to find the antiderivative of whatever is in the middle, which in this case is 4x to the 9th. This function that's in the middle, the 4x to the 9th, this is called the integrand. And this dx at the end plays two roles. One role that it plays is that it's kind of like the end parenthesis of find the antiderivative of the thing in the middle. It also tells us, the dx at the end also tells us that the variable that we care about is x. Sometimes you'll see dt, that means the variable in the middle is t, or ds, or d whatever. Whatever that letter is next to the d, that tells you what the variable is for the function in the middle, or also known as the integrand. This whole expression here we read as, or we say, the integral of 4x to the 9th. And then to answer the question, or to evaluate this integral, we write the integral of 4x to the 9th dx is equal to, okay, the integral sign and the dx say find the antiderivative of the thing in the middle. So we want to walk through our steps of finding the antiderivative. So I'm going to add 1 to the power. So I have x to the 10th, and I'm going to divide the number in front by that new power. So I have 4/10 x to the 10th. And then I add on a plus c because who knows, maybe there was some kind of a constant there. Now, I read this as the integral of 4x to the 9th dx is equal to 4/10 x to the 10th plus c. Another way to say that is 4x to the 9th is the derivative, and the original function was 4/10 x to the 10th plus c. Now, if you're super excited about fractions, you could simplify 4/10 to 2/5 x to the 10th plus c, but that's not really that important for us. Okay. Now, we have talked about finding an antiderivative in terms of these words right here. Add 1 to the power and divide the number in front by the new power. We can also write this in symbols. So for those of you that prefer symbols rather than written out words for how to do these types of things, our rule for x's raised to powers is that the antiderivative, oh, I want a k in front here too, the antiderivative of a number times x to the n dx is equal to, okay, the integral sign, the dx, say find the antiderivative of the thing in the middle. Our steps are add 1 to the power, so now I have an x plus 1, and whatever the number it was in front, I divide that by the new power, and then I add on a plus c. So for those of you that prefer formulas rather than step-by-step processes, here's your antiderivative rule for x's raised to powers. Now this is a perfectly legitimate rule with one exception. Think about if your power here, well, most powers this works. Even like x to the 1/2, this can work. But what if your power was a power of -1? If your n or your power is -1, this derivative rule will not work because you will divide by, or this antiderivative rule will not work because you're dividing by 0. So this rule works as long as x is not equal to -1. And we're going to talk about a different rule in that case. I don't mean x, I mean n. Okay, so as long as your power is not -1, in other words, if you don't have x to the -1, then this antiderivative power rule will work. Okay, let's look at another example. So here we have the integral of 1 over x squared plus 3 dx. All right, the integral sign and the dx at the end say find the antiderivative of the thing in the middle. Now, just like with derivatives, some of the strategies that we use with derivatives will work here. For example, when we take a derivative of 1 over x squared, before we take the derivative, we first rewrite 1 over x squared. So I'm going to do that here as well. So when I rewrite 1 over x squared, the price I pay is a negative on the power. So 1 over x squared is the same as x to the -2. And then I have a plus 3 and a dx at the end. All right, I haven't done any calculus yet. I've rewritten this using algebra. Okay, so now we are ready to find our antiderivative. So x to the -2, I add 1 to the power. Now, when I add 1 to the power, -2 plus 1 gives me -1. So my new power is -1. And I divide the number in front, which is 1, by our new power, which is -1. Okay? And then I write down the plus sign. And now I want to find the antiderivative of 3. Now, our rule up above does not work because we don't have an x attached to that 3. So what I want to think about is, what function's derivative is 3? And the answer is 3x, because the derivative of 3x is 3. So here our antiderivative of 3 is 3x. So I have 1 over -1 x to the -1 plus 3x plus some constant because I don't know if the original function had some number added on the end. Okay, so I can leave it as this, or 1 divided by -1 is -1. So we have -1x to the -1 plus 3x plus c. And this is our final answer. This says that if you take the derivative of this function inside the box, you will get 1 over x squared plus 3. Okay, so this rule, this idea that we used where, hey, we have a number here and we want to find its antiderivative. Well, the antiderivative of 3 is 3x, and there's nothing special about the number 3. If you have any number like k, if k is any number, then the integral of a number by itself is that number times x plus the generic constant. Okay, so for section 12.1, we have two antiderivative rules, which are really just undoing derivative rules that you've learned in the past. To find the antiderivative of x raised to a power, we add 1 to the power and divide the number in front by the new power. And to find the antiderivative of a number sitting by itself, we tack on an x. All right, in part 2, we're going to see an example of why we might actually care about these antiderivatives. But for now, that's all. Thanks for listening.